This problem has to do with stress concentration, so I want to work this. Here we have a load of 8,000 newtons coming this way, and obviously we'll have 8,000 coming back this way. Now all we need to remember when we have stress concentration factors is to go back to the equation. I'll do that in black. Is that K is equal to the max stress divided by the average stress. And then we can say that K times the average stress is equal to the max stress. Okay, so what I recommend first is determining where your failure points are going to be. And you want to look at all areas. Here, you possibly could get failure through here because you're going to have high stress concentration here. And here, right here at the base of the radius, you could possibly get a failure. So, because that's a small cross section, so you need to find out what the K values are here. So first one we'll look at here. Alright, so we'll come look at that. And now you're going to come down here, you're going to look at the ratio between W versus H. Okay, in this case W is going to be the width. W is equal to 40 millimeters. H in this case is going to be the thickness, so the thickness of this is 20. So that gives you a W over H value of 2. Alright, and then what you want to look at here, you got R over H, so you want to look at that. R divided by H is equal to the radius. And the radius in this case is going to be 10 over H. And H again is going to equal to the value of that, which is 20. That's going to give you 1/2. Okay, you come down here, you find 1/2. We know it's going to be right there. So what we can do is basically draw us a line at 0.5 up through there. And now you want to find the value that has a W over H of 2, which is going to be this line right down here. You're going to come down here, and right in there is going to be your value. I'll do that in red actually. It's kind of hard to find that curve, but right in there. So your stress concentration is going to be somewhere around 1.4, 1.41. So K is equal to 1.4 or 1.41. Alright, so we can find out what the stress is right there. All we have to do is find out what the cross-sectional area is. So we know the area of this, called A1, is going to equal to the thickness, which is going to be 20 millimeters. I'm going to go ahead and change that, do the unit conversion. So 1, 2, 3, that would be 0.020 would be equal to that. And now we need to multiply it by the thickness, and the thickness of this is 5. Alright, that'll give us a cross-sectional area there. 0.02 times 0.005. It's 1 times 10 to the minus 4th. And that would be meters squared. Alright, so now all we have to do is drop down and take our load, 8,000 divided by 1 times 10 to the minus 4th. Okay, that calculation gives us 8. 1, 2, 3, 4, 5, 6, 8. Let me count those again. 1, 2, 3, 4, 5, 6, 7, 1, 2. So it would be 80 megapascals. Okay, now that is equal to the average stress. So now to find the maximum stress, you take 80 megapascals, multiply it by your concentration factor, approximately 1.4, 1.41. and that gives us approximately 112.8 megapascals. Okay, I think the solution manual used 1.4 instead of 1.41, but that's the only difference. Let's get rid of that too. Just look at that real quick. Yeah, they use 1.4, but that's where that comes from. Alright, so that would be the stress at that end there. Now you want to come back and look at this cross section right through here. Again, find the area of that. So we have a hole cut out. The hole has 20. So we'll call that A2. A2 is going to equal to the width of that, which is going to be 40 minus 20. Again, that is in millimeters. So we'll just multiply that times 10 to the minus 3 meters over 1 millimeter. And then we have the thickness. The thickness again is 5. So multiply that by 5. Put this all in parentheses. Millimeters times 10 to the minus 3 meters over 1 milli. That right there would be the cross-sectional area of that. That gives me 20 times 10 to the minus 3 times 5 times 10 to the minus 3. Again, that gives me a cross-sectional area of the same thing, 1 times 10 to the minus 4th meters squared. Okay, now we got to find out what the concentration factor is going to be on that one. Again, all you're going to do is come down here. It wants to know what the ratio is of R over W. R in this case is the radius of the circle, which in this case we have a diameter of 20. So we can say that R is equal to 10. W is this entire thickness. W in this case would be 40. So that gives us 1/4 or 0.25. We come over here, 1, 2, 3, 4, 5. So it'd be, say, right in there. All we have to do now is draw a straight line up. We find out where that would hit, which would be in right about there. We come right back over and our value, and again, you're making a fairly good estimate. We got 1, 2, 3, 4, so 2.2, so 2.3 would be right there, or let's say 2.3 there, 2.35, probably 2.37 or something like that. Extend this down. So K, do it in black. Oops, do it again in black. K here would equal to 2.37. Okay, on this value here, the solution manual uses 2R over W, which is incorrect, because this is R over W, so 2.37 should be the correct stress concentration factor. So then you find your max stress is going to equal to 2.37 times your load, which is 8,000, divided by your cross-sectional area, 1 times 10 to the minus 4th. Run that number, 2.37. 1 times 10 to the minus 4. And that gives us a value of 896. 1, 2, 3, 4, 5. So that gives a value of 189.6 megapascals. And that would be your correct solutions. So right here would be your max stress. So if you're looking for a failure mode, your failure mode would occur right here. Okay? Alright, best of luck.